Hello and most welcome to Heidegger 1118. Presently south of Gothenburg in Lindome. That would be something like 20 kilometers south of Gothenburg. Not far from the coast. Thank God we finally got some rain. It's still very warm. I went for a walk. Still sweaty, but the weather is becoming more clement. Next week we're going to enjoy a little less heat, more in the vicinity of 20 degrees. More fitting for the season, I'd say, than the previous week's ghastly temperatures. I will continue to strive down the alley that Judy Currywan has paved so eloquently and elegantly. Getting to understand how this opens up both for Heidegger and Heraclitius at the same time. There is most definitely a lot of common ground to be covered here. I'm just going to give some general notes here to get you started somehow. One is that Judy Currywan uses a modern concept of information. This is not the Saussurian or the logico-positivist or the analytical philosophical concept of information as something hanging in the sky. No, this is information that is in some cases equal material. And once more, I mentioned this 20 times now, once more, this is Åge Bohr and why he got so frustrated when people started to talk about existence. What we should talk about is the information. You could actually say that we want to talk about the material, but not a reduced material to information, to zeros and ones, but the material of physics, and not the Milesians, but people like Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Franz de Broglie, Bohm, Wheeler, De Witt, Wegener, Ernst Wegener, without a doubt. It's also the insights of Gödel, the later Ludwig Wittgenstein, the whole lifetime and beyond, I would say, of Martin Heidegger. Why beyond? Well, he only in writing came to the conclusion of paraconsistent logic. And that is enough for him, of course. He had an understanding, but it was never explicit, so he couldn't tell anyone. That continuation is found in Graham Priest. It's also in another form found in Nagarjuna. But I won't mention Nagarjuna too often. He is bound to be misperceived, just like Heraclitus. I think that's a very interesting parallel to be taken up in a lecture in the future. But there is a very interesting parallel between Heraclitus and Nagarjuna. Not so much because of sloppery or cheating or biasness, but if we take down Heraclitus or Nagarjuna to the clarity of modern language, the whole idea gets lost, everything. So it's not the people's fault, so to speak. To do the interpretation. It has a closer connection to how we think about clarity and how in our understanding it is always affected by the stance of existence, the division between logos and ratio, logos/ratio and mythos, and so forth. So I continue where I started yesterday in 117, and it's the first chapter of Judy Currivan's book named Information. This is going to be the last paragraph on page 27. We'll start by seeing how information is becoming viewed as being more fundamental than energy and matter, and indeed space and time. Along the way, we'll discover how the minutest Planck scale of our physical world, trillions of trillions times smaller than the quantum realm, is key to our developing insights regarding the primacy of information. And we'll appreciate that matter and energy move, and how they interact are basically laws of information. The concept of information, content and flow is starting to be used powerfully to describe physical phenomena at deeper and more all-encompassing levels than hitherto. The two 20th century pillars of science, the quantum and the relativity theories, are also being re-evaluated as informational theories. A development that is being seen as having the potential to finally bring together these as yet unreconciled perspectives of our universe. Yet, as we'll see, this is just the first step to a much more encompassing perception. One that not only aims to understand the completeness of the physical world, but also proposes a cosmology that encompasses all aspects of existence and experience, and seeks answers to deeper questions of not only how reality is, as it is, but also why. We'll start by seeing how information is becoming viewed as being more fundamental than energy and matter, and indeed space and time. Along the way, we'll discover how the minutest Planck scale of our physical world, trillions and trillions times smaller than the quantum realm, is key to our developing insights regarding the primacy of information. And we'll appreciate that information really is physical, and begin our journey to understand how it literally informs our universe, while at the same time transforming our view of what we actually mean by the term physical. Hooray! An incomplete revolution. About a century ago, all our notions about energy and matter, space and time changed enormously. Until then, since the time of Isaac Newton and other pioneers of science in the 17th century, energy was seen as an attribute of matter and motion, and space and time were viewed as being absolute in themselves, essentially separate from each other, and a passive background to the real stuff going on. In the late 19th century, however, the cracks created by baffling phenomena, such as the inability to account for the energy radiated by a hot oven, that could not be explained by the prevailing theories of time, appeared and led to the emergence of two revolutionary new approaches in physics: relativity theory and quantum mechanics. These theories show that Newtonian physics wasn't wrong. In fact, we still use its principle in rocket science, as well as for a multitude of everyday purposes. It's just that classical physics is incomplete. The revolutionary breakthroughs brought about by relativity theory and quantum mechanics expanded upon Newtonian mechanistic principles, revealing that these latter were an approximation at our ordinary experience level of a more comprehensive but radically different understanding of our universe. A universe where energy and matter are complementary expressions of each other, and where dynamic fields of influence replace the notion of apparently separate objects and hitherto unexplained action at distance. Furthermore, space and time are relative to each relative to the position of an observer, and we can only consider them as invariant in their combination as four-dimensional concept of space-time. But just as Newton's insights 3 centuries before were only partial, so the scientific revolution of the 20th century was too. For the quantum theory that describes the physical world at tiny scales appears basically incompatible with the theory of relativity that describes it at massive scales. Fundamentally, quantum theory has no notion of time, and the space-time and gravity of relativity theory aren't quantized. In attempts to resolve their differences, much research has focused on developing a quantum description of gravity, with clues emerging from the study of matter under extreme conditions at the beginning of our universe and in black holes. Yet, despite some 80 years of trying, the two theories still remain stubbornly unreconciled. As if this wasn't enough, astronomical measurements of unexpectedly high speeds of galactic rotation, first convincingly reported by Vera Rubin in the 1960s, show that something that has become known as dark matter, only measurable by its gravitational effects, is indeed to keep the visible stars in their orbits and prevent them from being flung outward. Since then, dark matter, most commonly proposed as being an unknown, weakly interacting but massive subatomic particle, or WIMP, has been shown to pervade our universe. Beginning in the 1990s, measurement of the rate of expansion of space has also revealed that instead of slowing down as expected, it's actually accelerating, a situation currently attributed to the existence of so-called dark energy. While there are a number of candidates for this cosmological constant, that appears to be an inherent tension in the fabric of space-time itself, none are as yet proven. Neither of these two dark and utterly unanticipated components of the universe are as yet understood, but in constituting a currently estimated 95% of all its energy and matter, they relegate the two foundational but as yet unresolved theories of 20th century science to describing a mere 5% of physical reality. So where do we go from here? As was the case in previous scientific revolutions, it's in the seeking to deal with such apparent differences, inconvenient, anomalous, and exceptional phenomena that will open the door to our greater understanding and an even more comprehensive view of the world. It may, however, well prove to be the case that dark matter and dark energy will be able to incorporate within the expanded bounds of 20th century physics. For me, it's the quest not only to reconcile them, but also to respond to the deeper question of why quantum and relativity theories appear so adamantly opposed to each other, that may prove to be instrumental in profoundly revolutionizing our understanding of the physical world. So where do we go from here? As was in the case in previous scientific revolutions, it's in seeking to deal with such apparent differences, inconvenient anomalies, and exceptional phenomena that will open the door to our greater understanding and an even more comprehensive view of the world. It may, however, well prove to be the case that dark matter and dark energy will be able to incorporate within the expanded bounds of 20th century physics. For me, it's the quest not only to reconcile them, but also to respond to the deeper question of why quantum and relativity theories appear so adamantly opposed to each other, that may be proved instrumental in profoundly revolutionizing our understanding of the physical world, as well as our understanding of consciousness and the nature of reality itself. Doesn't sound bad. Even though the technological potential of these two theories has been exploited, other questions such as why and how the act of observation renders a quantum entity real, and what non-local connectivity, which Einstein called spooky action at a distance, really means, have largely been relegated to the sidelines of research. It is only now that the deeper clues, while they are still embedded within quantum and relativistic phenomena, are being considered and rooted in a far more wide-ranging and much deeper perception of how the whole world is co-created at all scales of existence. I think Einstein would be pleased. This emergent understanding of informational physics, however, while based on leading-edge scientific discoveries, represents a radical challenge to mainstream science. Thankfully, though, it's the power of the scientific method and its practical and unbiased approach that will compel mainstream science to follow the experimental and experiential evidence, regardless of an entrenched worldview or theories that attempt to make sense of it. Accumulating evidence from discoveries and insight in the past few years across a far-reaching range of disciplines, allied with a dramatically different approach to theoretical paradigms, is progressively describing our universe in terms of holographic information and ushering in a new 21st century scientific revolution. The potential of this radical new perspective is far greater than its ability to profoundly transform our perception of the physical world once again. As we'll go on to explore, because it's realizing that non-physical and multi-dimensional information is required to understand our universe. This emergent vision will bring about perhaps a more fundamental revolution in our comprehension of ourselves and the whole world than ever before. And I completely agree. This is an absolutely new thing. And could we say it's cornered by three things: chaos / fractal theory, Mandelbrot sets, Julia sets, and so forth, quantum mechanics, and the new Heraclitus coming up once more. The progressive recognition that scientific laws can be redefined and expanded in terms of information goes back to the 19th century study of thermodynamics. This is the branch of physics that investigates heat and temperature and how they relate to energy, work, and entropy. Previously, thermodynamics was the most commonly understood as the measure of order or disorder in a system, but it is now being viewed more fundamentally in terms of its information content and flow. From his study of the behavior of gases in the late 19th century, Austrian physicist and philosopher Ludwig Boltzmann predicted the existence of atoms and molecules. He was opposed by the majority of physicists at the time, and his opposition contributed to the deterioration of his already fragile mental state, leading him to commit suicide in 1906. And I think that happened in the Dalmatian coast, then belonging to Austria. His death was even more tragic, as within a couple of years the reality of atoms was confirmed and his theories were vindicated. Well, it goes to show that the resistance to atoms and molecules was so strong that people even committed suicide because of the resistance. In the middle of 20th century, in his study of communications, in other words, the transportation of information, IBM scientist Claude Shannon showed that the mathematical formula that describes the entropy of energy of gas in thermodynamic terms and the information content of a system is exactly the same. The very simple but hugely important equation that connects entropy with both energy and information should soon become as iconic as Einstein's famous equation linking energy and matter. And it certainly stands alongside in its importance. In this equation, S equals K log W. S stands for entropy, K is a constant named after Boltzmann, and log W is essentially the logarithm of energy states or information content of a system. As we'll see in the past few years, this equivalence of information and energy and the relationship with the concept of entropy, the equation for which is inscribed in Boltzmann's memorial, is revealing that information is actually more encompassing and fundamental, indeed expressing itself in complementary ways through the conservation of energy and matter, and entropically through the flow of time itself. In 1666, the University of Cambridge temporarily closed as a precaution of the plague then raging through the land. A young Isaac Newton, sheltering at his home in the tiny Lincolnshire hamlet of Woolsthorpe, used his time very well. In addition to his studies of optics and development of calculus, the mathematical formulation of change, it was here that Newton really did see an apple fall from the tree in his garden, as he later told his biographer William Stuckley, and which led him to discover the law of gravity. Some years later he was able to show mathematically that the rules of elliptical planetary motion, observed by Johannes Kepler earlier in the 17th century, obey the same law. By doing so, he proved that gravity not only pertains on Earth, but also that it governs our entire solar system, and so, by implication, pervades our entire universe. Indeed, all fundamental laws of physics are universal, in that they apply throughout our universe, regardless of circumstances of space or time. Such universality seems so obvious to us that we tend to overlook its enormous significance in revealing the all-pervasive and intrinsic interconnectivity of our entire universe and all phenomena that manifest within it. No subsystem, whether an elementary particle, a person, a planet, or a galactic cluster within our universe, is or can be completely isolated. Everything at scales of existence is being progressively discovered to be inherently related by informational content, flows and processes, as well as we'll see as we investigate further. This isn't just basic data, but all-pervasive informational patterns and relationships. We often use the word random to describe a lack of configuration or order. Yet, as theoretical physicist and philosopher David Bohm is reported to have said in a 1987 interview with holistic researcher and author David Peat, randomness is assumed to be fundamental but inexplicable and unanalyzable feature of nature, and indeed ultimately of all existence. However, what is random in one context may reveal itself as simple orders of necessity in another broader context. While they indeed may be probabilistic phenomena at the quantum level, and indeed at all scales within our universe, they aren't random or based on chance, as often portrayed. They act accordingly to the probabilistics within a range of possibilities that are dependent on the information they embody. Indeed, as the emerging view of the cosmic hologram is revealing, nothing in our universe is ultimately random. Everything that manifests in the physical world emerges from deeper and ordered levels of non-physical and informed reality. Information is physical. A couple of years ago, when I fell down a flight of stairs and slammed into a brick wall at the bottom, badly breaking my arm, my entire body screamed in pain, and the first physical world felt very well. Physical. It wasn't the moment to remind myself that all that we term physical is essentially 99.9999999% nothingness, and the rest is excitation patterns of energy and information. This fact doesn't just reflect the vast distances between planets, stars and galaxies, but the innate spaciousness of quantum scale realm. The familiar metaphor of an hydrogen atom, where if the single proton of its nucleus is represented by a basketball, and its single orbiting electron is then around 3 kilometers away, offers a visual image of this lack of materiality. Even more insubstantial, atomic nuclei actually comprise fields of influence within which quarks, the fundamental entities that make up nucleonic protons and neutrons, are deemed, according to the current standard model of quantum field theory, to be point particles. In other words, they have no internal composition or essentially spatial extent, or they have one that is too small to be measurable by current techniques. This too is the case for electrons and indeed all so-called elementary particles that are viewed as being the most basic constituents of energy and matter. With such transitory basis for our notions of what's physical, it's only the so-called Pauli exclusion principle, named after the Danish physicist Wolfgang Pauli, that prevents the atom of our bodies from coalescing with the matter of our surrounding. This principle states that no two quarks or electrons can occupy the same quantum state, that is, being in the same place at the same time with the same quantum attributes. This rule not only governs the chemical behavior of atoms, giving rise to the elements of the periodic table and the great diversity of properties, but also in preventing the subatomic components of atoms from approaching each other too closely, accounts for the essential stability of matter. In the past few years, the emergence of M-theory, the successor to multiple string theories of the 80s, aims to reconcile quantum mechanics and gravity, replacing the zero-dimensional point-like particles of the standard model with vibrating one-dimensional strings, which in M-theory are associated with holographic boundaries called branes. Yeah, I think that's a very good development. None of the philosophers of the Western Hemisphere has ever sort of questioned the idea why materia should be point-like. It's an absurdity that has never been put under the microscope or anything similar. Why has that never ever happened? Why would matter be point-like? It would take 3,000 years until that was questioned, and that was questioned in the M-theory. And one-dimensional strings are an option instead of that. It's not even a hypothesis, it's a hypothesization made by Greeks, never ever to be questioned even one singular time. It's absurd. It's beyond belief. Couldn't one say that? Why should matter be point-like? Auger did, but it didn't become fully expressed until M-theory. And it's 100% the idea in common man today in the Western Hemisphere. Matter is always point-like. This is why the example previously given here, that it's so extraordinary that the atoms are mostly space. Well, it is that if we assume matter to be point-like. But if we disregard that, if we put the idea of point-like into question, we start to see that it's an enormous hindrance in going about in the world. And I can assure you, none of the other cultures outside the Western Hemisphere, including, of course, the Middle East and other affected areas, do think matter as being point-like. The prakriti of the Indian thinking is material, yes, but it's not point-like. It leads to a lot of absurdities. For instance, this is not a book, it's a collection of atoms, as Democritus would have it. And I'm not criticizing the theory, I'm criticizing the idea that it's never been questioned or opened up, because it feels narrowed, myopic, shut mind-like. There is no openness in that thinking. It is closed. It's closed. And of course you can open up in other areas, but I think that closedness of the point-like nature of material reality is devastating. And it causes most harm to materiality itself, secondary to other things. But it runs havoc in the system. And to further the case, no atom has ever been observed. Yeah, there are pictures on the net. Yeah, go Google. Go picture Google if you want to. But those are created by the machinery. They are a side effect. It's a little bit like the Higgs boson. Without the Hadron accelerator in Switzerland, there would never be a Higgs boson, or any other boson for that matter, or any gluon or any fermion, or you have it. The idea of point-like nature of reality is a bit like Limited Incorporated by John Searle. It's the preaching of limitation, and it's also the preaching of unquestionable, or even worse, unpronounceable dogmas that pervades Western thinking. We can take them up to the surface, but just by naming them we make them stronger. So we need to be careful. Nature likes to hide, and atom is a way of non-hiding, bringing it up into the all-pervasive light all over. And by doing so, we make materiality much weaker. We destroy our understanding, and information goes out of the window, and I would say matter as a whole goes out of the window. It becomes reduced to one singular small thought, and it blocks understanding of what matter is. It will become clearer later on, where we go in further into Mandelbrot sets and so on, which show a more true picture, or at least an alternative to the point-like description of reality. Well, we continue with the Wolfgang Pauli principle. It states that no two quarks or electrons can occupy the same quantum state, that is, being in the same place at the same time with the same quantum attributes. This rule not only governs the chemical behavior of atoms, giving rise to the elements of the periodic table and the great diversity of properties, but also in preventing the subatomic components of atoms from approaching each other too closely, accounts for the essential stability of matter. In the past few years, the emergence of M-theory, the successor to multiple string theories of the 80s, aims to reconcile quantum mechanics and gravity, replacing the zero-dimensional point-like particles of the Standard model with vibrating one-dimensional strings. And I bet you everyone who reads this will perceive the strings to be made up by zero-dimensional point-like particles. Stir away from that. It will not happen by an instant. You need to retrain your minds. It will not happen directly. And you need to be persistent in retraining the mind. And that this could be a first opening up, because you need to see quantum mechanics as an exercise with a goal of changing the thinking into more openness, more possibilities, and seeing the old view as shut down or limited incorporated. Although M-theory first conjectured, and its name coined by Edward Witten in 1995, and other competing theories are offering progressively deeper insights, all of them merely replace one ephemeral basis of fundamental physicality with other similarly ghostly alternatives. As we'll see later, only by our considering the will-o'-the-wisp nature of physicality in terms of the more fundamental nature of information are we able to perceive the primordial realities from which our experience of physical reality arises. In 1931, Max Planck, one of the greatest pioneers of quantum theory, stated that I regard consciousness as fundamental. I regard matter as derivative from consciousness. Listen to that. Many other scientists before and since, including Einstein, have expressed similar views. In 1991, information theorist Rolf Landauer was the first to explicitly declare the physical and fundamental nature of information, that is itself inherent in all notions of consciousness. We'll explore this crucial insight from three main angles: how quantum behavior can be explained in terms of information, how information and the fundamental physical concept of entropy are vitally interconnected, and how all physical laws and natural phenomena can be re-expressed informationally. In all three approaches, we'll see how all universal physicality can be considered and restated as processes, states, and flows of information. Further evidence that information is an intrinsic attribute of all physical systems was first suggested by Hungarian-American physicist Leo Szilard, who theoretically showed that there is a minimum amount of work needed to store one piece of digital information, or bit Landauer, or bit. Landau then showed that the erasure of any such bit of information increases entropy by precisely the same amount. Kt ln2, where K is Boltzmann's constant, T is temperature, and ln2 is the natural logarithm of 2. a rule now known as Landauer's principle. Finally, in 2012, physicist Antoine Beru, Eric Lutz and their colleagues were able to experimentally prove Szilard and Landauer's predictions by measuring the dissipation of heat from the erasure of one bit of information. Wow! Reporting in the journal Nature, they succeeded in verifying the link between the role of heat and temperature in the relationship between energy and information, and so confirmed the essential physicality of the latter. Next paragraph, quantum information. Considering information as fundamental offers us deeper understanding of why matter and energy are quantized, and also of the wave-particle complementary nature of quantum entities. However, before we move on to considering quantum theory in informational terms, let's begin by briefly reviewing these two key cornerstones in energetic terms as its pioneers understood them. Before their insights, classical physics considered our universe as a continuum. It was by attempting to explain something apparently as simple as how hot oven radiates heat that led Planck to propose the first theoretical quantum perceptions. The problem was that the classical electromagnetical theory of heat and light maintained that such radiation from its most idealized source in a so-called black body should occur on a continuous and unlimited basis. This conclusion resulted in the total radiated power being theoretically infinite, which was a nonsensical result and one that bemused physicists of the time referred to as the Ultraviolet Catastrophe. It was Einstein, though, taking and applying Planck's insights, who solved the problem. He was awarded the Nobel Prize in 1922 for this solution rather than for his most famous discoveries relating to the equivalence of energy and matter and the relativity of space and time. Einstein's explanation came about through his studying of problem related to the ultraviolet catastrophe, that of the so-called photoelectric effect, where incoming light can dislodge electrons for the surface of a metal plate. In classical theory, where light is perceived as being continuous, electrons should be able to be freed by shining more intense light onto the plate or doing so for a longer time. However, this isn't what he observed. By realizing that only light above a certain energetic threshold of frequency is able to free the electrons, regardless of the intensity of or duration of the light beam, Einstein postulated that light travels in discrete packets or Planck theoretical quanta, whose energies increase with frequency. So a light beam of progressively higher and so more energetic frequencies, say from red to blue and then ultraviolet light, is shown onto the plate even if at a very low intensity. Individual quanta have the requisite energy to bump electrons out of metal. Wow! Einstein's genius was in recognizing that the photoelectric effect as a result of quantization also explains the conundrum that Planck himself was attempting to understand, the finite radiation of a hot oven. Here too emitted energies are expressed, not as the classical continuous and unlimited spectrum of wavelengths, but as discrete quanta each having a specific energy and so totaling a finite amount. Quantization of energy and matter, however, is only one side of the complementary relationship between waves and particles that lie at the core of quantum theory. While taking different stances on what it actually meant in terms of nature of reality, in the early 20th century, pioneering physicists such as Niels Bohr, Werner Heisenberg, as well as Einstein and Planck, recognized that physicalized matter and energy could be regarded as both waves and particles. For example, the wave-like energies of electromagnetic waves of light also behave as quantized particular photons. In 1924, the French physicist Louis de Broglie then took the next logical step and realized that all elementary particles also exhibit wave-like behavior, albeit at very small wavelengths. It was in 1926 that, in a series of scientific papers published in an intense period of only few weeks, Austrian physicist Erwin Schrödinger produced the equation named after him that has become foundational for understanding how the mechanics of quantum entities behave, as well as their wave-particle complementarity. Schrödinger's deceptively simple equation is made up of a series of variables within a single wave function that incorporates all the possible quantum states of a system in terms of probabilities, which are spread throughout the waveform. The equation's most general form shows how the relative probabilities of these states evolve through time. Only when observed or measured do the probabilities then become a specific state in the physical realm. Rightly seen as being one of the most important scientific insights of the 20th century, and honored with a Nobel Prize, Schrödinger's equation reveals the most complete amount of information that is possible to know about a physical system, not only at quantum scales, but also every level up, and including our entire universe. Schrödinger's wave function, though, predicts the likely physical manifestation of a system when observed in terms of the underlying probabilities of how it evolves over time, not in the physical realm, but in the so-called complex plane. For many years, this was seen as a mathematical abstraction that happened to be very useful in predicting quantum behavior. But more recently, as we'll see in further detail later, the complex plane, and indeed other non-physical spaces and dimensions, are being ever more recognized as a deeper level of reality from which the physical appearance of our universe emerges. Complex planes, we spoke about that Tuesday in the quantum meeting. I'm sorry to say, for you who speak only English or read only English, it's in Swedish, but it has to do with imaginary numbers. Covers all of real numbers and all of imaginary numbers. It covers all of real space, observed space, and all of unobserved space. That could go for time, could go for knowledge, information. Having briefly described the quantization of both matter and energy and their complementarity wave-particle attributes, we can now start to reframe them in terms of information. Fundamentally, as the need to resolve the ultraviolet catastrophe of classical physics showed, a continuum has the capability of literally carrying infinite information. Our universe, however, is finite. Within it, time literally began some 13.8 billion years ago at the Big Bang. And given our understanding that physical space and time can only be considered as a combined entity of space-time, finite time must correspond with finite space. A finite universe can only embody finite information. Then there thus needs to be a mechanism for the essentially unlimited potential of the non-physical wave function to become finitely manifest. Quantization, with its innately discrete nature, is such a mechanism, enabling finite information to be expressed within space-time. We're familiar with the idea of the ones and zeros of bits being the digital building blocks for computerized data processing. But such bits are the simplest expression, the literal building blocks of all finite information, enabling its processing with the minimum energy and maximum stability. Combining bits, rather like building a house out of bricks, enables any and every possible outcome, and multiple outcomes, to be expressed as efficiently as possible. Essentially, the energy and matter of our universe is quantized because information is digital, and thus quantized, and information is quantized because it's the most effective means for its communication. Let me read this very, very important paragraph once more, and do remember it because it holds the key for one step up the ladder to understanding the contents of the book, which is, I would have to see now, it's a groundbreaking summary of what's going on in quantum mechanics, plus what happened in chaos theory. And it's bringing in everything that happened in the mid-2010s. And that pushing everything a step forward beyond what we read earlier. But it's in the summarization. And I was so surprised that Judy Currivan has very, very few critics, and those criticisms are usually to the details. So the summarization in itself is very good depiction of what the current state is. It's putting together that information, that knowledge, which is so hard, and she managed to do that. Not until that is done, because it's massive, it's a lot. It needs also to be condensed to fit a book format. This is one of the problems by starting a new paradigm. The complexities of the new insights never ever are gathered like this. They are spread out. And when they are spread out, they don't have much effect. The effect comes when they are put together, and it's a little bit like starting a radioactive reactor. You need enough radioactive material uranium-235, if I remember correctly from my school, to have the process of nuclear energy to start. Even more so in an atomic bomb. There is a critical mass that needs to be reached. And I think that has been reached in the book of Judy Currivan. And imagine I almost missed it. By being biased. Sensible bias, I still think, but otherwise the amount of literature I would have to read and write about would be too extensive. I think the 60-70 books a year I've been doing the last few years is quite enough. And that not counting articles, small writings, YouTube clips, and other things, and things discussed, and things I get from other people, of course. Will never cease to be thankful for you all, of course. So I'm going to repeat it. Essentially, the energy and matter of our universe is quantized because information is digital and thus quantized. And information is quantized because it is the most effective means for its communication. Very important. Here we have realization in 2 words. From the viewpoint of information, we can also better appreciate how wave-particle complementary enables energy matter to be observed in one or another form. The key is in how the definite state of the entity is observed and measured. In other words, in how information about it is accessed. Essentially, the realization derives from information interaction between the entity and its environment. Until that moment, the Schrödinger equation describes the evolving probabilities and potentialities of both aspects of its wave-particle nature. This understanding of how realization comes about has been tested by ever more sophisticated means over the past few years. A preliminary and key question was answered in 2012 in a groundbreaking paper that reported the findings of a so-called quantum delayed choice experiment. The experiment aimed to resolve whether quantum entities behave either as a wave or a particle depending on the circumstances, or whether they are always both until they are measured. When dependent on the type of measurement, they switch to one form or the other. For the first time, the research team was able to construct a measuring process that included a high level of non-local behavior, enabling and revealing photons to exist in a simultaneous state of both wave and particle, as lead author of the paper Alberto Peruzzi of the University of Bristol in the UK confirmed. Their non-local entanglement enabled the photons in the experiments to delay the choice of whether to behave as particles or waves. The non-locality effectively replaced the delayed choice of an observer, which would have triggered either the wave-like or particle-like form to be exhibited. Knowing that quantum choice to prompt either its wave-like or particle-like aspect does indeed arise from observation, scientists have still sought to determine why the quantum entity sometimes then behaves as a wave while at other times as a particle. And still, scientists being scientists, they've tried to see if there's some way of observing both at once. In 2004, and then with a more refined experiment in 2006, Iranian-American physicist Shahryar Afshar baffled his colleagues when he appeared to violate the either wave or particle behavior by seemingly demonstrating wave-like interference patterns of light, at the same time measuring the paths taken by the quantum particles of light, photons. In a subsequent experiment in 2012, a team of German scientists also set up an experiment that seemed to verify Afshar's findings. In 2014, though, a collaboration of Canadian and US physicists including Elliot Bolduc and Robert Boyd reanalyzed the challenge posed by the apparent findings and discovered a flaw that comes back to how information is accessed. They realized that the setup for any experiment must choose how it obtains information through observation and measurement. That is, how the experimental apparatus interacts with its environment. For example, a choice can be made to measure the experiment environment aspect with the best information about the path, or alternatively, to choose that with the best visibility of the interference fringes of wave-like behavior. To properly test complementarity, the measurements must be equally sensitive to all possible states of system, a requirement known as fair sampling. When this requirement was applied to a German team's 2012 experiment and Afshar's earlier analysis, the 2014 team determined that they violated the fair sampling rule. It's now incumbent on any further future testing of wave-particle complementarity to ensure that such fair and unbiased measurements of information are rigidly enforced. The 2014 findings confirm the evidence of all past experiments that point to wave-particle complementarity being an intrinsic attribute of space-time. The progressive understanding, though, of how information underlies and pervades the appearance of such complementarity is crucial to realizing how the environment and observer are integrally interconnected with any and all experiments. Remember Alice and Bob's, extend that to the whole world. We are interconnected. Taking it apart will cause 1/1,000,000% deviation. But that's enough. Remember the butterfly effect, because the butterfly effect was decisive, not the 99.9999% of certainty. It's the butterfly effect and nothing else. We'll get closer to that later on, but it should be established already here now. This is what we're getting to. And I'm not usually the one to give away the solution, but in this case I think it's good because it keeps you on track that there is a reward coming to you. In other words, there is no separate objective reality, and the entirety of our universe is an integrated, coherent and informational entity. There is literally no environment apart from the consciousness of the observer. And I think that's a restatement of what Planck said in 1915 or 12, and I restate it once more. There is literally no environment apart from consciousness of the observer. Before we go on, and at this point in our investigation, let's briefly consider how, prior to the emergence of the informational approach and holographic perspective, quantum physicists had come up with a hypothesis that I think will be seen in the future as one of the most unhelpful diversions in the history of science. This is going to be good. Save this. I did not know this coming. I didn't have the time to read so far in the book. This hypothesis is called the many worlds interpretation, or MWI, and is one of a number of versions of the concept of multiverse. The MWI describes the nature of reality as consisting of infinite parallel worlds, embodying infinite alternative histories, presents and futures, and maintains that all are equally real. The MWI was a contrasting response to the interpretation of experimental evidence that the observation of an event affects its outcome, the so-called, you should know by now, Copenhagen interpretation. As we'll see, more and more evidence is accruing that not only supports the Copenhagen perspective, but also expand it to be the perception of an informationally based, integral, non-locally interconnected, and ultimately intelligent universe. However, in 1957, and before this 21st century perspective gained traction, American physicist Hugh Everett proposed the scenario of the many worlds interpretation. In the 60s and 70s, it was popularized by the fellow US physicist Bryce Seligman DeWitt and entered the speculation of science fiction. Many movies to be done on this theme. Too many, I would say. Now this is the point. I just took a break to make it even stronger. This is so important, and I would say MWI, the many worlds interpretation, is the thrust that puts you out of reality. It's important to understand that. Even if you don't hold the belief of MWI, it's important to understand it, because that thrust is still present, even if you reject it. Listen to this, it might make it clearer. The MWI seeks to avoid the underlying and all-pervasive pervasive presence of information, intelligence, and consciousness in manifesting reality by the premise that every possible outcome of every quantum scale event really exists by branching off somehow into an infinity of other universes. Essentially, it aims to banish any deeper consideration and involvement of consciousness from understanding the nature of reality. It pushes everything away to a distance. And that thrust is still present even if you don't acknowledge many words' interpretation. Yes, it's very unhelpful, but at the very same time, I don't agree with you, Jude Corrivan here. It is helpful to understand the reason for this theory. Much more. It's very hard to get any further without understanding that tendency in our thinking. Otherwise, why would such a ludicrous theory be proposed or thought about? It doesn't give any information, could never give any proof. Why construct such an air castle? This is the important question, not criticizing it only. It's bound to fall anyway, so no need to criticize it. A theory without information doesn't have any stamina to it. So you don't have to criticize a person that says the world doesn't exist. That would be ludicrous. It was just hitting with your fist in empty space. Don't do that. But do understand the tendency, because you are bound to find that tendency within yourself. And if you don't find it, you cannot understand it, know it, go further. You will be stuck. Why do I say that? Because we know by now, everyone in the Western Hemisphere has this foundation. It's been present for 2,500 years. It is established in all our doings, in our attitudes, in our Stimmung. So here is a clue: you need to find it within yourself. Well, you can find it, maybe it's a better phrasing. Not only, I continue here, not only is there no mechanism for such a scheme, but it also violates pretty much every principle of physics and adds a level of inexplicable and unnecessary complication without any rhyme or sensible reason. Just as any quantum system exists as an evolving state of superposition of probabilities until its realization, so too does the information of its possibilities exist as superposed so-called qubits, quantum bits, until realized as specific digitized bits. This enables us to expand the understanding of information to quantum information that integrates with quantum theory and expands it beyond being a description of energy and matter, but being more fundamentally expressed in terms of information. Qubits are the informational building blocks embedded within the probabilities of the Schrödinger wave function, just as digitized bits are then the information specified by the it of its realized single state. Unlike bits that can only exist as or either 0 or 1, or any dualistic on-off expression. Qubits can be superposed in any combination of these two states. Until they interact, are observed or measured in some way, there is no way to access any information about qubits. However, once they devolve to a specific state and are then described by bits, there's also then no way to retrospectively access information about their superposed states prior to such measurement. It's a very eloquent and elegant way of putting it. Now you see the development from superposition going to definite state, and so important to understand the order here. Without understanding the order, you're bound to fall into a pit. These attributes of qubits have spurred accelerating research into quantum computers. Their ability to exist simultaneously in many states of superposition enables them to process information at vastly greater speeds than a digitally based computer, and the inaccessible nature of such superposed states can be used to create effectively unbreakable cryptographic codes. We'll shortly continue to reframe the phenomena of our universe in informational terms. But to do that, we first need to begin our exploration of the minutest and most extreme scales of energy, matter, space, and time. And now we enter into the Planck scale, named after the first one to realize that the ultraviolet catastrophe must take us to the next level. The primary laws of our universe incorporate a number of unchanging physical constants. Three of these universal factors govern the relationships between energy, matter, space, and time. These are the speed of light, the gravitational constant, and Planck's constant. Respectively, each is associated with special relativity, gravity, and quantum mechanics. As Planck was the first to suggest, these constants can be combined to define a scale of measurement that is integral to the workings of our universe. This scale, arising naturally from the interplay of universal forces, appears literally to represent the possible limits of physical reality itself. The extent of its measure of space, or Planck length, is an astoundingly tiny 10 to the log minus 35 meters, which is as small when compared to the size of a soil amoeba, as such a tiny organism in Earth is to the size of the entire universe. Wow. The Planck scale, or time, which denotes the time taken by light to travel a Planck length, is an almost equally unimaginable 10 and the level to minus 44 seconds, which is even more extraordinary when it's compared to the age of our universe, since the Big Bang around 10 up to 17 seconds. The Planck scale of energy matter denotes where quantum and gravitational forces become equivalent as in the background conditions at the beginning of the universe and within black holes. The Planck mass of 10 to the minus 10 kilomern is the maximum mass for a point-like elementary particle, and equivalent to a black hole with a diameter of 1 Planck length. The Planck scale, though, is far more than an interesting scientific curiosity, for as we will discover, Investigation at these extremes, including the entropic informational content encoded by black holes, are not only revealing that the nature of space-time ett ögonblick. So we soldier on here. The Planck scale, though, is a far more than an interesting scientific curiosity. So, we can finally continue. Let's see here. The complementary, it's to do with the pixelation, the Planck scale and the Planck time and the Planck length shows that the universe is pixelated. And here is the connection between matter and information. Since time, space and scale all are pixelated, it shows that information is the most basic. For how would we otherwise know about matter? There is no other way to transform any knowing about it. So the pixelation shows that at the bottom it must be information. That's one way of understanding the whole thing. I'll continue here. For as we'll discover, investigations at these extremes, including the entropic informational content encoded by black holes, are not only revealing that the nature of space-time itself and the relativity theory that describes it are best understood in informational terms, but also that the informational bits entropically embedded by space-time are pixelated at the Planck scale. Planck scale, very important. The complementarity nature of wave-particle phenomena is also revealed by consequential restrictions on the ability to measure associated pairs of physical attributes beyond the Planck scale. The energy of an entity and the time of its measurement and the momentum of an entity, its mass multiplied by its velocity, and its position in space. These limitations are wrapped up in a basic premise of quantum theory called the Heisenberg uncertainty principle. As with so many terms coined by science, the so-called uncertainty principle is poorly named, for it is rather a principle relating to indeterminacy. Its deeper insight is of the innate complementarity nature of certain universal physical attributes and their measurements. The more exact the one measure is, the less precise its complementary partner. There is a fundamental limit to the accuracy of one to the other that relates to the Planck scale. This innate boundary has nothing to do with our ability to take specific measurements, but is essentially caused by, and further clue to, the pixelation of space-time at that minute scale. informing the whole world, from the Planck scale upward to the entirety of our universe, we're beginning to appreciate how everything we call physical reality is literally made up of information. Recent experiments have also shown that quantum informational behavior isn't limited to the quantum scale. Exactly the same types of wave-particle complementarity and superposition have been demonstrated for entities as large as organic molecules. They are so enormous when compared to the tiny quantum level that such evidence is revealing that there is actually no difference between the informational behavior of quantum entities and that of microscopic ones. The reason why larger scale phenomena don't appear to exhibit quantum scale behavior is that it's progressively more difficult to isolate them, and the information inherent in them from their interactions with the wider surroundings that we incorrectly view as being separate from them and the term environment. For as we've seen, it's accessing such information that manifests the phenomena, any phenomenon at any scale, from the superposed probabilistic state to a specific state of realization. Just as quantization and Planck scale pixelation have perfect informational attributes for the manifestation of the physical world, so do holograms and the generic nature of the holographic principle. Holography was invented, or more correctly discovered, in 1947 by the Hungarian-British physicist Danis Gabor. While man-made holograms are rudimentary, as we'll see later, advances in the holographic technologies are nonetheless offering deeper insights into the nature of cosmic hologram. For now, though, it's enough for us to note how holographic characteristics are ideal for the recording, storage, processing, and retrieval of information, both on a distributed basis and non-locally. The interference pattern of light that make up holographic projections are able to incorporate enormous and unmatched amounts of information. In addition, at its smallest coherent scales, every part of a hologram contains the informational content of the whole, effectively distributing and storing it non-locally and self-replicating the macrocosmic whole within its microcosmic elements. Bearing in mind what we learned so far, let's now turn to examining the larger scale attributes of our perfect universe and begin to explore the informational foundation of space-time itself. 2. Instructions. Instructions tell something how to do something. This planet came with a set of instructions, but we seem to have misplaced them. Civilization needs a new operating system. A cite by Paul Hawken, activist and author of Blessed Unrest. Just as for baking a perfect chocolate cake, making our perfect universe, which after around 13.8 billion years of evolution has arrived at the point where we can enjoy cake, requires the essential initial instructions, conditions, ingredients, a recipe and a container. We'll now explore how the necessary instructions, the algorithmic programming that literally inform the creation of space-time, and the energetic informational principles that perpetuate throughout the lifetime of our universe, and that are the foundation for its evolution, were present from its first moment. Until the 1920s, our universe was deemed unchanging and infinite by most astronomers. However, in 1927, a Belgian Catholic priest named Georges Lemaitre and a scientist put forward the idea, confirmed observation 2 years later by Edwin Hubble, that instead of being invariable, the universe is expanding. Nonetheless, astronomers such as the UK Fred Hoyle still viewed it as being ultimately infinite, coming up with a now disregarded steady-state model that theorized that matter continually forms to offset the expansion and retain a constant and ultimately eternal state. Hoyle compared his proposal with a contrasting theory of a specific and thus finite beginning, for which in 1947 he coined the name Big Bang. So Hoyle came up with the Big Bang theory. He was a UK chap. The Big Bang model, however, made a testable prediction that from an enormously hot start, as our universe expanded, it cooled down and should accordingly be filled with remnant radiation from that early era that would now be measurable as very cold and radiating at microwave wavelengths. Only in 1965, when the Bell Telephone Laboratory engineers Arno Penzias and Robert Wilson accidentally discovered this so-called cosmic microwave background, or CMB, which is, for instance, also called Michael Bellman, when they were bothered by excess noise in the radio receiver they were building, was the prediction confirmed, which led to the Big Bang becoming generally accepted. Initially, they thought pigeon poo in the equipment was to blame for the noise and went to great, presumably messy efforts to remove it. But when the noise persisted, other scientists realized that it was the residual energy signature dating back to around 380,000 years after the Big Bang, when our universe first became transparent to light. Not only the CMB presence, but also the analysis by NASA's Wilkinson Microwave Anisotropic Probe, WMAP for short, of tiny irregularities within it, provides further evidence that our universe is finite. In 2003, WMAP's examination of the patterns of slightly hotter and colder spots that represent ripples in it, rather like minute waves in the ocean, show that longer wavelengths were missing. An infinite universe should include wavelengths of all lengths, whereas a finite universe will have a cutoff such as that measured. While there are cosmologists who still maintain that despite its finite birth, our universe will expand to infinite spatial extent and eternal temporal duration, as we'll continue to see, such a view is at odds not only with the fundamental logic, but also with the laws of physics and increasing observational evidence. To conclude, however, that the space-time of our universe is finite is not to presume that the entire cosmos is, nor indeed that its infinity is only expressed at the physical level. In past decade or so, a plethora of theoretical models of other and indeed all possible universes forming a so-called multiverse have been proposed. These have attempted to address various contentious issues, including the apparently very specific and special nature of our universe, and most usually by viewing it as being a random event within an infinity of other random events, all equally without meaning or purpose. As we already began to perceive, to understand the physical realms not only of our universe but also any multiverse scenario calls for a deeper perspective of the ordered information that underlays and pervades them. Toward the end of our exploration, we'll consider certain multiverse theories in informational terms too, to assess the extent to which they may offer us an expanded perception of an infinite and meaningful cosmos. However, in the meantime, we'll continue to focus on our universe. We have an exciting journey ahead. Take chapter 3 from the book Heraclitus and Derrida, A Pre-Socratic Deconstruction. And the way particle duality can also be expressed in this way. Chapter 3, The Illogic of Logocentrism. War is the father of all and king of all, and some has shown as God, others as men. Some he has made slaves, others free. Polemos, pandon, men, pandis, patis, esti, pandon de basileis, catus men theos, edixe tus de anthropos. Tus men doulos epice tus de Eleftheros. Eleftheros must be free then, okay. Well, pardon my Greek. We have all seen the foregoing discussion how Heraclitus begins his philosophical discourse from a critical stance when he questions epistemological assumptions and writes in suggestive but, according to modern standards, relatively undetailed ways about the particular subjectivity of human ways of knowing, including the insignificant role of irrational and other unacknowledged forces at work in the human production of meaning. Let us now explore in greater detail Heraclitus' critical analysis of the production of meaning, in which he doesn't tell so much as he shows how theories of cosmic order are conditioned by particular characteristics of human subjectivity. Our theories of the cosmos are overdetermined by the structural properties of the linguistic systems and binary oppositional logic. The Heraclitean critique of epistemological and intellectual paradigms is important not only for its characterization of the state of affairs concerning understanding of the cosmos, but also because it sets the groundwork and conceptual terminology for the content and form of his own positive prepositions regarding a theoretical account of cosmic and psychological structures. Because of his tendency to express himself in cryptic, oracular tones, it would be a mistake not to consider carefully one of Heraclitus's most memorable expressions with respect to our reading of his idiosyncratic signifying. Oanas uto madeon estitien delphos ute lege ute crypte alla semane. Every philosophical system, the Lord whose oracle is in Delphi, neither indicates clearly nor conceals, but gives a sign, semene. Every philosophical system has an organizing vision, a conceptual framework with fundamental divisions that constitute the set of values and terms from which the rest of the paradigm unfolds, and upon which all subsequent claims depend. What Heraclitus does to great effect is to put philosophical conceptual frameworks to the test with the very reason they champion. He assesses the validity of predominantly theories of cosmological structure by interrogating the a priori assumption and the source of reasoning that enables such determinations. In this chapter we examine those propositions which expose the nature and the limits of the classical logocentric account of rational thought and knowledge, including the logical paradox upon which logocentrism relies. Many of his texts examine the logic of logos by bringing attention to how difference between things is understood and to the effects of differentiation. Central to his discourse is his critique of the overzealous philosophical emphasis on distinguishing and naming discrete objects, and the insufficient acknowledgement of the actual relational aspects between these elements. In effect, his discourse asks, at what point is the intellectual investment in reifying difference an irrational distraction from a larger sense of connectedness and relationship? Question. For Heraclitus, it is in examining the limits of distinguishing difference that we find out what we know about something, and more importantly, by what means we know it. In particular, Heraclitus makes a significant and scandalously underappreciated contribution to philosophical thought when he shows how knowledge, organized by principle of radical binary opposition, is misleading, unnecessarily reductive, and heedless of the complexity of complementarity and fluid relationships. Heraclitus shows how the methodological reliance upon structural opposition both enables comprehension and articulation of the logos, and also distorts the resulting characterization of cosmic order. In his unorthodox argument about the unity of opposites, Heraclitus proposes that recognizing the congruence and dependence between binary opposition is, at the very least, equally important for understanding the unity of logos as determining their differences. In keeping with this view, he will describe the nature of cosmos and the human soul, psyche, as a harmonious tension and as an ongoing flux of changes. This is very similar to what I read earlier, and is also divergent. And by stretching out the understanding and allowing for parallel thinking, I think parallel thinking is the most important here, because I propose many times that we look at the primitives of Namibia Desert, the Kalahari Desert, or the ones living in the Amazon basin, the Yanomami people or the Eskimos, or the people of the Nagaland in India, or the indigenous people living in Borneo and so forth. But I say we can reach the same status of naturalists by starting to have parallel thinking, having two lines of thinking at the same time, something made possible by the understanding of quantum mechanics. Can you see? By making it possible to having two things being complementary, not contradicting each other, neither adding to each other, not being two sides of the same coin, but being complementary, we can start to have parallel thinking. And we will stop to see thinking as a natural tendency. We'll see it as information and something that we can change. And we can change the character of thinking as well. This is not possible before quantum mechanics, and I would say also the Mandelbrot set. But once you understand it, we can dwell into a completely new way of thinking that allows two parallel lines. Something that not even Damasio thought to be possible. And I think most people today abhor and say you can't text while driving a car and so forth, or having a conversation on the mobile while having a conversation with the third person. But this shows that that will be possible to develop. But it's never ever an inborn habit. You're not born with thinking. Thinking is that you learn very early on, and it is a way of treating information. And by ignoring that it could be changed, the order, the causality, the relationship, you will not access thinking, and thereby you can't change it. You will be someone who's just pointing outwards, not being able to point inwards. That is the force of parallel thinking. You can think and at the same time observe your thoughts and thereby change them. This is not the automated reflective consciousness that only reacts. No, this is a moving consciousness. This is the wave-particle duality. That means awareness starts seeping into reality. And that changes everything. From that time onward, when parallel thinking starts, you will explore a completely new area, a new avenue of thinking. And I think it's connected to what Edward de Bono, the late Edward de Bono from last year, meant when he said parallel thinking. But I never got it that way, and I think it's impossible to have parallel thinking until one understands quantum mechanics, because that's the opening up of information. It does, that insight of quantum mechanics will change you, because no longer is thinking separated from matter. Until that point, you will think all your neurons, all of your materiality is unchangeable, and therefore it will be unchangeable. You will not be able to affect it. And this is why most people have no possibility of collapsing in an aware way, the superposition. They will do it in a random way, and that random way of collapsing the superposition is very close to classical mechanics, an experienced classical mechanics, because you don't have any power or anything, you don't have any control. And that uncontrolled way is classical mechanics. So it's not only by mental understanding something. Take that away from your thinking concept. There is no such thing as mental understanding. When you understand something, you change materially as well. Matter is not disjunct from information or knowing. Just to think that will limit knowledge incredibly, and it will make it impossible for you to, in a aware way, change the superposition. We have classical mechanics for a good reason, because 99% of the population in an unaware and random way collapses the superposition. Therefore, establish an experience that the world actually is outside of their control. So it's the hen and the egg once more. And I think it becomes clearer as we read Heraclitus that he, I wouldn't say warn, but he takes as a foundation the Milesian philosophers of nature, but he wants to go further. But he also points to, if you stop in that binarity and not understand that the binarity comes from something more encompassing and more fundamental, you will stop to be able to change. And then you will turn into something static yourself. Because it's not only by understanding, it's your posture that changes when you are classical mechanical. And going to quantum physics will change everything with you. It will make your veins different, will make your attitude different, will make you more movable. Otherwise, you're still in classical mechanics. You will collapse the superposition in completely random ways, because that's the experience of classical physics. The randomness that you actually experience and is actually there as well. This is not a made-up thing. You can have random collapses of the superpositions. You're simply not in control. And we will get more into that when we come into awareness, that most people today are unaware, but not in the way you met early in New Age and psychology, not at all like that, because they are already limited to classical mechanical physics. Quantum mechanics need to come into the picture, otherwise it can't change. And you will not accept, I would not accept, a change if it's not proven by science, because science is the big judge these days. It pervades everything we're thinking about reality. And that goes for everyone. No one is accepted from this. How could they be? It's only this new possibility of parallel thinking that actually is proposed indirectly by quantum mechanics, that possibility comes to fore. And I would say, in different manners, that is proposed both by Jude Caravan and Heraclitus, but in completely different ways of saying it. And I think we need both. We also need the help of Heidegger to have a threesome or a triad. With the help of a triad, we can go further. A holy trinity, in a way. And I say thank you very much and have a very pleasant afternoon.